All right, this is 7-4's homework. We got the worksheet and a little bit of textbook work. So jumping right in at 7-4A. So in 1 through 5, we got multiple choice. We're going to tell if the situation described is exponential growth or decay or constant increase or decrease. So these are curves going up and down or straight lines going up and down. So number 1, there are 5% fewer patients with the disease. So first of all, anytime you see a percent, we know this is exponential something because it's not going to be a consistent increase every single time because it's going to be 5% of a new number and then 5% of a new number, whether it's going up or down. Okay, so the amount that it actually goes up every single time is going to be different because 5% of each new number is going to be different. And this says fewer, so obviously that is going down. This is exponential decay. Number 2, with better techniques, farmers are able to increase, so we're going up, their output 3% each year. So 3% of what it was, 3% of what it was. That's going to be a different amount every single year. So that is not constant. That is going to be exponential, and we're talking about growth. Number 3, each year there are exactly 30 fewer students in the school. So it doesn't matter how many you started with, it's 30 less, 30 less, 30 less. That is a constant decrease. That would form a straight line on a graph. Number 4, single elimination tournament. Half of the teams are eliminated in each round of play. So let's say you started with 100. Half are eliminated. Now you have 50. Half are eliminated. Now you have 25. So that's not constant. It's the same in terms of it's half, 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 but the number of teams being eliminated each time is changing. Okay, you took 50 away from 100, then you took 25 away from 50. It's a different amount. This is going to curve. Again, we're going down. This is exponential decay. And number 5, every time Joan took the test, her score increased points. Now, don't love this one, right? Every time, it doesn't say exactly how much it increased each time. Okay, it should say her test score increased 10 points or 5 points, something like that. That would make this a better question. But they are looking here for constant increase. This is not a percent change or anything like that. Okay, number 6. We've got this company. They receive hundreds of applications. Their selection process is to review all applications. They get rid of 50% of them at a time. So take all their applications. Let's cut them in half. Then we'll look at them all again, cut them in half. Look at them all again, cut them in half. Just keep eliminating half of them until you're left with your final applicants. So n equals the number of times that half the applications are discarded. So letter A, write an expression in the form b times g to the n to describe the number of people left after the applications have been reviewed n times. So we don't have much information here. We don't know the starting amount, so we're just leaving b alone. And we don't know the number of times it's happened, so n is going to be in this. But we do know that it's being cut 50%, half. That's 0.5. And that's being raised to the number of times. So you're going to start with a certain amount, and you're going to take half of it this many times. So now we can go ahead and plug in. If 512 people apply for a job, so 512 is going in for B. How many are left when n equals 4? So it's 0.5. Oops. And you're not raising to the n, you're raising to 4. And you're going to run that right through your calculator. So your starting is 512. You have gone through the process 4 times of cutting them in half. How many applications are left? Just run that through your calculator, and that would be 32 people are left. All right, number 7 now. We're given this information. We're going to have to plug it in. We're going to create a scatter plot. We talked about our x values can't be these years. They're too big. Okay, when we start plugging in for n or for x, it can't be in the thousands. So we are starting with year 0, and then each year following that is going to be measured in how far it is from the original. So 1988 is 1 from 1987. 1989 is 2. Now these are counting straight up. And so they're going to get numbered straight down. You have to be careful though. Sometimes they don't count right up by 1s or 2s. They're all over the place. So we do need to be careful. All right, I'm going to go ahead and just reset my calculator so we have a fresh start here. And so I'm going to go to Stat and Edit, and I've got to input all of this. So I'm doing 0 all the way down. Let's see, I went all the way down to 17. I'm going to go over and be real careful here. 17 is my first, 33, 55, all the way down, being very careful that I get these all correct. Okay, and it's always good to double check, make sure you have an equal amount in each column. I do, so unless I just hit a wrong number going in, and this should be correct. So we're going to go ahead and create a scatter plot. And before I go ahead and hit graph, I know my window is going to be off. So I'm going to go to window here. I got to go from 0 to 17. So I'm going to start with 0. And I like to actually go a little bit higher than this number so that my last point isn't actually right at the top of my screen. Give it a little bit of room. So I'm going to go to 20. And I'm going to count by 2s. Okay, you can count by 1s. That would be fine. Now my Y minimums. This one's real important. So I got to go from 17. So I'm going to start at 15. So it's just below this one. And I'm going to go up to 9,000 or 8,500, something like that. And I'm going to count by a nice big number of 1,000. Now I'm going to go to Y equals. I'm going to turn my plot on. And now my graph should show up very nice. There it is. Okay, so it says create a scatter plot. Does it appear to be linear or exponential? You can see this is curving up. That's exponential. All right, using regression, we're going to find the equation that fits the data. And so I'm going to hit stat. I'm going to go over to calculate. I'm going to go all the way down. Since this, I don't want to use number 4 because this is not linear data. This is exponential data. So I'm going to hit number 0, and it's going to go ahead and give me the information I need here. So Y equals. I'm going to go ahead and round this off just for the sake of room here, but it is better the more you go. So if you went 4 decimal places, that's perfect. I'm going to round it here just like the answer key did. 27.4 times 1.44 raised to the x. Okay, so there's my equation. Now we're going to go ahead and use that equation to predict how many stores there will be in 2013. So first of all, I have to figure out what number goes with 2013 because I can't plug in 2013. I have to plug in how many years that is since 1987. So you could just go ahead and subtract 2013 minus 1987. So that's 26 years. So I'm plugging 26 into this. 27.4 times 1.44 raised to the 26. And if yours was slightly different because you rounded differently up here and you had more decimals, then your number is actually better. Okay, but we're plugging in. That's the important part. Now, what year will there be more than 20,000 stores? So we're already well over 20,000 here, right? And if you look at 2004, we're not quite to 20,000 stores yet. So it's going to be somewhere in between year 17 and year 26. So you could start plugging in year 20, year 21, different stuff like that and try and figure it out and just guess and check. But my favorite option here is to go to your Y equals and plug this in, 27.4 times 1.44 raised to the x, and then go to my table. If I go to my table, my Y values here, going down, and you can see right here between year 11 and year 12, we're going to have, oh, I almost messed up there. I thought this was going over 20,000. That's 2,000, right? So we're going to keep going. Now we're at 19,000. Here it is. So in year 19, from 1987, we're going to cross over from 19,000 to 20,000. So it's 19 years from 1987, and that would be the year 2006. So straight from the table, you can find that. So turning the page, number 1 on 7.4b, we have the half-life of beryllium. Half-life means it gets cut in half, is 13.81 seconds. Means no matter what mass or how much beryllium you have, half of that decays in 13.81 seconds. Half of it goes away, whatever you started with. So n is going to be the number of times that has decayed. So it's not measuring an actual, well, it is measuring an amount of time, but this is how many times we've had a half-life, okay, which is going to be how many times 13.81 seconds has passed. So we're going to write an expression in the form b times g to the n to represent this. So we don't know the starting point. We don't know how much mass we have to start. We do know that it gets cut in half. So that's 0.5. And then that's going to be raised to however many times 13.81 seconds has gone by. So if the original mass is 16 grams, so plugging 16 in for B, what mass of the sample remains after 41.43 seconds? So we have to figure out how many times this has passed in 41.43 seconds, because every 13.81 counts as one half-life, or 1n. So I'm going to take 41.43 and I'm going to divide it by 13.81. And you can see that fits exactly 3. So in 41.43 seconds, it has gone through 3 half-lives. So 3 is what's going to go here. And I'm just going to run this through. 16 times 0.5 raised to the third. And the answer there is 2. So you're left with 2 grams. All right, letter C. If n equals 5 and there's 1 gram remaining, what was the original mass? So we don't have B. We're going to be given all the rest of the information. So we know that it's going to equal 1. We don't know what B is. We know it's half-lifing, so that's always 0.5. And we know n was 5. So if you take a look, they told you all of this is going to equal 1. We just don't know how much we started with. So we're going to set it equal to 1, and we're going to go ahead and solve this equation. So first thing I'm going to do is simplify. 0.5 raised to the 5th is this. So 1 equals B times 0.03125. So I'm multiplying B times this to get 1. So all I got to do now is actually divide by this. So 1 divided by 0.03125 is 32. So 32 grams is what you started with. All right, number 2, the value of the car goes down by 22% the first year and then by 11% for the next 8 years. So the first year we're going to have to calculate on its own. And then the next 8 years we can use our formula. So if a new car costs $28,055 originally, so first we got to take 22% off of that. So 28,055. If you're taking 22% off, it's 1 minus 22%, or 1 minus 0.22. Okay, that's going to be 0.78. So if 22% goes down on the first year, you now have a car that's worth 78% of what it used to be. So 28055 times 0.78. And so it's worth $21,882.90 after year 1. Now it's going to go down exactly 11% for the next 8 years. So now we can go ahead and run it through that equation. So 21,882 is what we're starting with, and then it's going to go through 8 years of going down by 11%. 1 minus 11%. That means it's worth 89%. If it goes down 11% each year, it's worth 89% of what it was each and every year for 8 years. So since I already have this in my calculator, I'm just going to hit times 0.89 raised to the 8th, 8,614, and we can round this to 40 cents. That's how they did it in the answer key, but if you left it as 39 cents, that's fine. Not worried about that. All right, again, we're going to go back to identifying exponential growth and decay, or constant increase or decrease. Scientist discovers that for a given species, the population is cut in half. Okay, if it's cut in half, that's a different amount every year because it's half of a new number and it's going down. So that would be exponential decay. Okay, as she aged past 60 years, she lost exactly 1/4 of an inch every 5 years. So it's 1/4 of an inch, 1/4 of an inch, 1/4 of an inch. That's a slope. It's going down 1/4 every 5 years. That is a constant decrease, straight line. Number 5, Each year, the student population grows by 50, up 50, up 50, up 50. That's a positive slope. That's a constant increase. Number 6, clothing store has a sliding scale policy. The first week an item is in the store, it's discounted 10%. Then the next week, discounted 20%, then 30%, then 40%, so on and so forth. So this one's kind of tricky. You want to say exponential decay, right? Because first of all, it's not constant. It's going to be a different amount. But because it's a sliding scale, exponential decay goes down by the same percent every single week. 10% down, 10% down, 10%. If we have something changing here, that's kind of just all over the place. All of these are consistent in something. Okay, it's either decaying at the same percentage or it's increasing by the same amount exactly. This is all over the place. So this is actually none of these. It's not going to fit any of them. It would have to be going down 20% and then down another 20% and then down another 20% to be exponential decay. 7, gossip spreads through school quickly when every student tells 2 other students. Now, this sounds like constant increase, but it's not going up by 2 students and then up by 2 students and then up by 2 students, because each person who finds out tells 2. So those 2 people go tell 2. Well, now you've got 4, and then those 4 people tell 2. Now you've got 8. So it's actually doubling. Okay, so it is not increasing by the same amount. It's not up 2, up 2, up 2. Okay, it's up 2, up 4, up 8, up 16. Okay, so that is actually exponential growth. Number 8, she adds exactly 5 more stickers. Okay, that's constant increase. Percent, so here we're looking at growth or decay. A savings account earns 5% annual interest, which is added to the account. So 5%, and then 5% of your new amount, and then 5% of your new amount, and that is exponential growth. All right, last page on 7.4b. We've got this chart that we're going to have to plug in and create a scatter plot here. So if you still have all your data here, the easiest way to clear it out is you go up to L1 and you hit clear and enter, and L2, clear, hit enter, and it goes away. So again, we're not going to use the years. We're going to use these numbers that are given to us. Now, we're not going to start with 0 as 1984. They've already kind of told you how they want you to do it. We're going to measure everything from 1980. So we are starting with the 4, 5, 6 on all the way down. And we're going to go all the way down to 20. Okay, and slide over to L2. Now we got to put these numbers in carefully. All right, easy to make a mistake in there. Not sure if I did, hopefully not, but I do know that I haven't missed anything. I have the exact same amount in each one of these. So I'm going to go look at my window real quick. I'm going to go from 0 to 20. That's fine. My Y's, though, I'm only going up to 8,500, so I would miss some of this information here. And if I start at 15, that's honestly fine. You could start at 1,000 if you wanted to, something like that. But I do need my maximum here to go up past 11,000, so I'm going to put in 12,000. Count by thousands is fine. Let's go look at our graph. And I still have my old line. That line has nothing to do with this graph. So I do need to clear that out. If I go to my y equals, clear out that old line. All right, there's my scatter plot. Clearly that's exponential. But you could argue linear too. You could draw a line through the middle of this that would be pretty close. But this does look to be curving up. So using regression, we're going to find an exponential equation to fit the data. So we're going to hit stat, calculate. We're going to go down to number 0 because it's exponential. Enter, enter, all the way down to calculate, enter. And we'll go ahead and round some of this. So y equals, or a is 805. Now we are talking money here, right? So let's go 2 spots. 36 times 1.14. That's a good place to go to with the 0 next. Raised to the x. Now we're going to use our equation to predict the high close for 2009. Now we're going from 1980. So if we take 2009 and we minus 1980, so a lot of people would do 1984. You got to be careful. These numbers are all going back to 1980. That's exactly 29 years. So we're taking this equation and we are raising this to the 29th power. Run that through your calculator and round as needed, and it came out to 35,994. Okay, looking forward, predicting when will the close be over 13,000. You can see it's already pretty close to that. So you could try 21, 22. You could also, again, go to your y equals and plug in this equation, 805.36 times 1.14 raised to the x, and then go to your table. And we know that 20, it should be around 11,000. And you can see it's not exact because remember, this is a line of best fit. So it's not going to hit every single point exactly. So we want to know, when does it go over 13,000, or when would we predict that to happen? And so year 21, we're under 13,000. So year 22 would be where this happens. And from 1980, 22 years later would be 2002. Okay, so jumping to our textbook work, we are starting with number 6 in lesson 7.4. So we're not identifying what each one is. We're going to tell whether you would expect each exponential regression to produce a good model for the data. So is exponential good for this data? So letter A, to me, this looks like a straight line right down through the bottom. This isn't curving one way or the other. So I would say no. Explain your reasoning. Looks linear. Letter B, I think yes, absolutely. Curves exponentially. Letter C, looks like yes. This looks like exponential decay going down. And then letter D, I would say no. And to me, this isn't necessarily linear or anything. This is all over the place. No real pattern. Definitely not curving up or down. Okay, number 7. We're going to match these equations to these graphs. So starting with number 7, we have to pick which equation fits this. So first of all, we are starting up here at 8 point something. So we're not starting at 5.1. It's one of these. It's starting at 8.7. Okay, and it's either going down by 10% or it's going down by 42%. So 10% of this, if you just took 8.7, if you took 8.7 times 0.9 raised to the first, okay, which would be this one plugged in, you hit enter, it should be up at 7.83. Okay, and this jumps all the way down here to 3 point something. And so if we slide over here, 8 is going to be the one that matches up here with letter B, because we started at 8.7. We go down here. So I'm going to go ahead and jump forward here. 8 matches up with letter B because it starts at 8.7, and then 90% of that jumps down to 7.83. So clearly C goes with 7. And if you actually plugged it in, 8.7 times 0.42 raised to the first would get you 3.654, and you can see that's that right there. And so number 9, starting at 5.1, and then taking 10% off, 10% off, 10% off, little by little. Okay, that makes sense. And so that's letter A. Okay, jumping to number 12, we have to come up with our own problem that can be modeled so it shows that you understand the equation. So if y equals 72 times 1.08 raised to the x, you're starting with 72 with something and it's increasing by 8% because we're going over 100%. So I'm going to say something about money. You start with $72 and earn 8% interest per year. Again, you got to make up your own. We need to make sure that we're increasing by 8% starting with 72. So 13, we are starting with 14 of something and we're decreasing not by 65%. We're going to have 65%, which means we lost 35%. So let's see. I'm just going to make something up that starts with 14. So you have 14 ounces of water and you drink 35% of what you have left per hour. So it goes down 35% per hour. Again, you can make up anything for these. It doesn't have to match mine. All right, last one, number 14. The population of a city is 1,250,000. Write an expression for the population in y years under each assumption. So these are all going to be under y equals b times g to the x. What you begin with, and then your factor, your growth factor. So for letter A, population grows. So first of all of these are going to say y equals 1,250,000. That's your B. That's what you're starting with, times your growth factor. So it's growing 2.5%. So it's going over 1. So it's starting with 1 and then adding on 0.025 raised to the x. You could put y for year. Oh, actually, it specifically says y for years. So we're going to put y right here like this. And if you want to, now you can't use y here. Let's put p for population. It says write an expression, so you don't even have to have the equal sign for the equation, but it's fine. So for letter B, the population is decreasing 3%. So again, starting at 1,250,000, going down 3%. So from 1, it would be 1 minus 0.03. If you do 1 minus 0.03 or 100% minus 3%, you have 97% of what you did the year before. And then letter C, the population decreases by exactly 1,500 people per year. This is not a percent. This is not exponential. This is linear. Okay, y equals mx plus b form. We are starting with 1,250,000, and we are decreasing or minusing 1,500 people per year.